So Linnaeus classified organisms based on shared characteristics, like things with fur he put into the mammals, and things that look like snakes he called snakes, right? He classified them, and he once again gave them a binomial name. Every species got a two-part name, the genus and specific epithet, and he classified organisms in this nested classification system. When he did it, it started at kingdom, but we now include domains. Domain bacteria, domain archaea are the prokaryotes, domain eukarya are the eukaryotes. Kingdom Animalia, for example, phylum Chordata, class Mammalia, order Carnivora, family Felidae, genus Panthera, species Pantheropardus. So we can see an example of that classification system here. Now, as modern scientists, we don't just want to lump things, because, Linnaeus just lumped things how he thought they were created. Mammals were created and they have similar traits. But we understand now that things weren't created as they are now, that things change over time thanks to evolution. And we attempt to show that phylogeny, that evolutionary history, by drawing the relationships on trees like this. And then we can map on the classification system of Linnaeus on top of that. Although sometimes we find out that our Linnaean system was a little bit wrong, and we have to correct our classification once we build these trees of evolutionary history. So here we can see Carnivora, family, a genus, and there's lots of different genera here. So here's Canis lupus. Remember we saw the dog earlier, Canis lupus familiaris, but here's Canis lupus, the gray wolf, Canis latrans, the coyote. You can see that they are on this branch together. Let me go back. There's a branch here. So I want to point out how you look at these trees. This, like for example, this number 2 right here represents a common ancestor of coyotes and wolves. That's this branch point right here. And then the two species branch off from one another. The ends of these branches typically represent now, the modern era, and then back here is in the past. So we can see in the past at number 1 there was a common ancestor between wolves and badgers, right? If we go all the way back here, some of the first members of the order Carnivora were ancestors of cats, like the leopard, badgers, and wolves, okay? So these branch points are important. When we're looking at these trees, we need to remember what everything represents. For example, this great figure from your book shows this branch point represents the common ancestor of everyone on the tree. At least one of the common ancestors of everyone on the tree. There's more back here probably, right? Each horizontal branch represents an evolutionary lineage. Usually the length of the branch doesn't mean anything unless it's a special kind of tree where occasionally the branch lengths are important. Some of those will show time or genetic change, but typically the branch lengths on the ones we're drawing are not necessarily important. Any position along this line can represent an ancestor. There'd be like thousands of, hundreds of ancestors potentially along this branch. It doesn't mean we know them all, but if we find a fossil, we might go, oh, that's a fossil that probably fits in right here, for example. Okay. And groups like chimps and humans here, or in the last slide, like coyotes and wolves that share a common ancestor are called sister taxa. You can see that word here. Sister taxa are organisms that share a common ancestor that's not shared by any other groups. Okay, so humans and chimps are sister taxa. One last term I'm going to give you that you'll see, and it'll come up again later. In this tree, fish are the outgroup, meaning they are the first group to branch off on the tree, and they kind of allow you to put things in the right order. We'll talk about that more later. Another thing I want to mention is that at these branch points, which are also called nodes, N-O-D-E-S, nodes, the tree can rotate and it still shows the same relationship. It doesn't change the meaning of the relationships if those nodes rotate. And you can see the original tree here and another depiction there on the right. Which shows the same thing. So these, once again, are called nodes, and they represent a common ancestor, remember. But the tree can rotate there and it doesn't really affect things. So this tree shows the exact same relationships as this tree over here. These are the same. So here's a nice depiction of all of this put together. We can see different groups. Remember, any level of the Linnaean classification system can be called a taxon. So that could be a species or a family or a domain. You know, right there is a node, and taxon A and B, or I'm sorry, taxon B and C are sister taxa here. This taxon here is the basal taxon, which I'm going to refer to later as the outgroup. It's the first one to branch off from this common ancestor. Okay. Another word that I guess I might as well introduce you to is this word right here, a polytomy. A polytomy is a branch point where we don't know who branched off first, like this one right here. When they all branch off from the exact same point and they all come, you know, to the modern era, we don't know who branched off first. That usually a polytomy indicates that we just don't have enough data yet. This is a hypothesis. We don't have enough data yet to really understand what happened exactly. We can't resolve the relationships yet until we have more data. And this kind of tree can be used for lots of things beyond just studying evolutionary history. For example, your book discusses how folks selling whale meat, which is, you know, I'm sure there's lots of regulations on whale meat, and they might claim it's from one kind of whale, but we can do genetic tests to determine which whales that meat actually came from. And so it's useful for doing this. They've done things like this in the United States where folks claim that you're eating, you know, Atlantic salmon or something, and it actually is something from the Pacific Ocean. You know, you can figure out what you're actually getting at the store, and if it's violating any laws or ethical issues by testing their DNA and seeing what things are related to. Okay, so we've been talking about phylogeny, which is the study of evolutionary history, and we're building these trees, and oftentimes we'll call those trees phylogenetic trees. And you'll also hear me call them cladograms. All right, I know those are very different words, but let's talk about this science of statistics. Cladistics. Cladistics is a branch of taxonomy that classifies organisms based on common descent. And it has this word in it, clade. By definition, a clade is a group of species that include an ancestral species and all of its descendants. Okay? And all of its descendants. Another word for this idea is a monophyletic group, which we'll get to in a minute. A clade is an ancestor and all of its descendants, and that's what how we try to group organisms when we name them using modern cladistic techniques. So this involves phylogeny, okay? Clades can be nested within larger clades, so keep that in mind. So like a clade could be the mammals, and the mammals are chordates, right? So we try to make sure that our Mendelian classification groups, our taxa like phylum, class, order, and family, are clades. And sometimes we find out that we're wrong, that we have a group that's not a clade. For example, if you called, let's say you called snakes and legless lizards, we now know they're not closely related. Legless lizards, that's what that's supposed to say. And then here's other lizards. What if you thought snakes and legless lizards were closely related because they don't have legs, but you realize later that legless lizards are actually more related to other lizards? That would be an error, and you would have to redo your classification system. So we'll pick up with ideas like that in the next video.